Hi everyone and welcome to this new video. In this video I want to showcase how you can create a simple capture the flag challenge. So in this video we will go through all the various steps. We will start from the main idea, then we will sketch out a high-level implementation scheme. We will actually implement it in Python using Flask, and then we will discuss the intended solution and why it does work. As always, I hope this video is fun and interesting. If you find it so, please leave some feedback, subscribe to the channel, share this video and this channel with like-minded people to help me grow. Thank you very much and enjoy the video. So let's start our discussion from analyzing the main objective that I want to capture in this CTF. So every CTF, every challenge is based on a core objective idea. What it is that you want to teach. I mean, good CTF aims to teach something. They aim to teach something. Now, the focus, of course, can be put on different things. You can have a focus on the usage of a specific technology, the focus on a specific exploitation technique, or on a specific enumeration technique, or also on how to combine two or more different techniques that by themselves are like known, but the combination of those techniques can be interesting to analyze. Now, what about the CTF we want to create today? Well, the objective for our simple CTF will be the following. Explore the concept of unicode normalization, and specifically we want to explore how a badly and insecure implemented normalization process can lead to path traversal vulnerabilities, so to path traversal issues due to a badly implemented unicode normalization. So basically that's the idea. The idea is to talk about unicode normalization and path traversals. So let's go over the high level scheme, like how do we want our challenge to play out. This is key to do before actually implementing it because of course it takes some figure it out, it takes some brainstorming to understand what makes sense to implement before doing that. So let's start. Now, once the idea has been defined, it is time to sketch out how the challenge should work and what is the expected solution. Now, in our case, we will expose a simple web API with 4 different endpoints, and these are the following: register, login, write, and read. Now, register and login are used to implement a very lightweight and simple authentication system. So, both of these endpoints, they take in post with 2 parameters, username and password, and they allow the simple registration and the simple login of a user. And once the user registers, the data of course is saved in a database, in a local database, but this is not really the key of the challenge, it's just added stuff. Now the key of the challenge are these other 2 endpoints, the write and read endpoints. Now the write endpoint accepts a post verb, while the read accepts a get verb. In the post we take 2 parameters, the file name and the content. And this allows us to write a specific file with a specific content in a specific public directory. So we can imagine there is this public directory, it exposes a bunch of assets, and with the write endpoint we can write. Now, in this case, the security of our system depends on how we protect the public directory. Why is that the case? Well, because for example, if we have this /app/public, right? So if we allow the user to write into this directory, we must make sure that the user cannot write outside of this directory. Otherwise, he can access the other parts of the file system. So this is critical to implement. So this public directory is shared among all the different users of the application, and this is by design, and we do not authenticate this endpoint, just like this. And then we have the read endpoint, which takes a single parameter, file name, it takes a get as a verb, and it allows us to read a file from the public directory. The content read is then returned to the user, and this endpoint instead must be authenticated. Now, both the read and write endpoints will actually process the file name using a specific normalization algorithm known as NKFC. Now, both endpoints will also implement simple logic for checking against path traversals. The only difference between the 2 endpoints is in the order in which they implemented the 2 operations. So basically, we have 2 operations here. We have the operation of normalization, which we will discuss in a bit, normalization, and we have simple checks for path traversal, so like security checks. So we have these 2 operations that both endpoints do. The difference is going to be in the order in which they implemented the two operations. Because for the slash read, we will first check for path traversal and then perform the normalization, while in the write endpoint, we will do the opposite. First, we will perform the normalization and then we check for path traversal. Now, which of these two is going to be insecure? The answer is going to be the first one. Now, the insecure implementation is in the slash read. Why? Because a malicious actor is able to introduce unicode characters which initially they are not considered dangerous from a security point of view, but after normalization, they actually become dangerous. And this is because these characters are special versions of the slash character, right? So the slash character is used to separate directories in Unix based file system like Linux. Now, this can be a problem, right? Because the idea is that I'm going to have a character which is not strictly speaking a slash in ASCII style. It is a Unicode character. It's a weird form of slash. So when I do the security check on this weird form of slash, I will not consider it a slash. Therefore, the security check will be, okay, all good. Your payload is okay. Does not have anything malicious. However, after normalization, this weird character will actually be transformed to the slash ASCII character. And then when it's going to be used as a normal slash, and this allows a user to bypass the security checks. The flag is then found in the root directory of the project within a file named flag.txt. And basically, at the end of the day, this is going to be the intended solution. We will use the file name ... and instead of having ... slash, like typically you would do ... slash, we have ... these 3 bytes URL encoded, which represents a specific Unicode character that after normalization, this Unicode character becomes the normal slash. So when this payload is actually used, it's going to be ... slash flag.txt. So we're going to go back one directory, we're going to go from the public to the private directory, and we're going to read the flag. And it's important to sketch out the intended solution if it's like this simple. Now, of course, this is like a simple CTF, as I said, so this is not too hard to sketch out. But in general, if you want to create a challenge, this is a good habit to do. So now we can move on to the implementation phase. Now, in terms of implementation, we will use Python with Flask, as it allows us to implement simple web API endpoints without too much trouble. So here are all the commands that you can follow. I'm going to create the app directory. I'm going to cd into it. So actually here I already have. So let me just delete it because it's going to be just the old iteration. So I'm going to create the app directory. I'm going to create a Python environment with python 3-m Then I'm going to activate it. So bin amp activate this. I'm going to install the dependencies, Flask, and I'm going to freeze the dependencies into the requirements.txt file. Now, this requirements.txt contains all the different libraries that pip has installed. And this is useful for the reproducibility of the challenge, so that when we finalize the challenge, it's going to be easier to just deploy it whenever we want. And then we create a file called main.py, and this file is going to contain the main logic of our challenge. Then we make the public directory and we put the flag into the flag.txt. So now we have the structure of the challenge. Now at this point, we can go into the main.py and we can start to code our Flask application. And we can start with something as simple as this. So let's zoom in and explain what it does. Here we are just stating the interpreter to use, we are importing the Flask library, and we are creating a simple Flask application that takes a single route slash and returns an hard-coded string hello Flask. And here we're listening on port 1337. We put the bug true, but this is not really important for the challenge itself, and we listen on all network interfaces. So basically that's the idea for now. So let's go into notes. Perfect. So this is the first thing that we do. Okay, so now technically we can also just run it, right? We say Python main is started, and we also have the debugger pin, and we can just do a simple curl on our endpoint, which is 1337 slash, and look at this, we get hello Flask. down here below, we get a hello Flask. Here we get the thing logged in the database, so that's good. Now, at this point, we need to create the core endpoints for the challenge, the endpoints that will have the vulnerability. So let me go into this other tab. Here, I'm going to have main on one side and these nodes on the other side. So here, I'm going to import the Unicode data library because this library implements the normalization algorithm that we will use, which is the NFKC algorithm. And we will write these two endpoints, so the write and the read. So let's analyze the logic for both. So we have write post, read get. Here we take the input from the user, file name and content, and here we do the main stuff. So here we are normalizing the data using the NFKC algorithm, normalization algorithm, and then we are checking for malicious payloads. Now this approach is not really robust, but in this case it's gonna be fine. We check if our file name contains either a slash or a dot slash in the file name. In this case, we return a security danger string saying, look, this input is not valid. This is also known as a data validation using a blacklist approach. So in a blacklisting approach, we want to avoid essentially all the malicious input. So we want to characterize the malicious input. Now, blacklisting is a limited approach because sometimes we're not able to capture the full scope of the malicious input, the full scope of the malicious domain. But in this case, it's a simple challenge, so it will be fine. After we did the check, we construct the final path using the public and the file name that was given by the user. Then we open that path and we write our stuff, and then we return a broad file. Now in the read, we do a similar thing. We, instead of writing with open path W, we say open path R, read. And instead of doing first the normalization and then the security check, we actually do the opposite. First, we do the security check, then the normalization, and then we use that path. Now, this is actually vulnerable, and it is vulnerable because when we do the security check at this point, I can put a Unicode character here, and after the normalization happens, this Unicode character is going to be mapped to a slash, which means that when the file name is actually used, here this file name will contain malicious slashes. So I can have, for example, dot slash multiple times, and this is not gonna get caught in this, essentially. And of course, here, even if I put a dot in this check, by exploiting this Unicode normalization, I can also bypass that thing. Now, in this case, I'm not even putting a dot here, so it's a little bit easier. But even if I put a dot here, it's gonna be the same kind of attack. It's just a little bit more complex with respect to the specific payload. And so we have these two endpoints. So let's go back to our nodes now and let's try out this basic application. So let's try out the basic vulnerability. So I have started my server. So let's start it again I just do Python main, and this server is started listening on port 1337. And here to test out the basic vulnerabilities, I can proceed as follows. First, I write a first curl with write mode, and I'm writing a file name hello.txt with a content word. And it said, look, I wrote this file. And if I check in the public directory, notice that I read this hello.txt. And if I actually read this file, I see that, look, in this file contains the word word. So that's good. I can also read this file, right? By doing a read with the file name in the input parameters. And I get the correct content of the file. Perfect. Now, at this point, if I just try to read the flag like this, it's going to say security danger, because it's going to notice that, look, in this payload, we have the dot slash. Now, to actually exploit this, I need to encode this slash using Unicode normalization. So the payload to win actually is going to be this one. It's going to be EFBC8F. If I do this, notice that I actually get the flag because I bypass the check and I'm able to read the flag.txt, the file flag.txt. So this is a first approach. Now, to actually continue the challenge, however, I also want to implement a very lightweight authentication system just to add a little bit more complexity, like really nothing too much, but it can be fun. So we're going to create this model.py, and in this file, model.py, we're going to put all this content, and now I'm going to explain what it does essentially. So what does this file contain? Here we have SQL Alchemy and bcrypt. So these are the libraries we use to wrap over our database, and bcrypt to hash the user password. Here we define the class that contains the user table data. We have a simple ID, username and password, extremely minimal. And then we have the wrapper over the database, authDB. We are using a simple SQLite database, and here we are implementing the registration and authentication endpoint. So in the registration, we save the new user. In the authentication, we check if the user exists and if the password given by the user during login is the same as the one saved in the database with the function bcrypt check password. So it is an extremely minimal wrapper to implement a lightweight authentication. So how do we actually integrate this to our dependencies? Well, we have to install more dependencies. We have to install SQL Alchemy and we have to install bcrypt. We have to install bcrypt and we're gonna freeze again to update our dependencies. And then we have to modify the main.py. This main.py we have to modify because we have to add the authentication. So specifically, we have to import the authDB wrapper. We have to instantiate an object of such class. And then here we have to add the register and login endpoints. Register and login endpoints. And notice that I left. So look at this. Register and login, simple endpoints. Here we take the user input, we register it. If everything goes well, we say okay, otherwise failed registration. Same thing for the login. If the login goes well, we add the username to the session of the user. So basically, that's the idea. And then here, look at this. There was a to-do left from the previous iteration that said, okay, I actually want to authenticate the read endpoint. So let's go to our notes and let's add this if check to authenticate the endpoint. Now, this controller is going to check if the current user is authenticated, if it has a cookie session, essentially, within the Flask context. And so basically, we are done. So we are done. We can just execute it once again, and we should have all our things going on. So at this point, we can analyze the intended solution, like what should a user do to understand this. Now, first of all, this challenge is meant to come with the code. So you are meant to see the code and create a local copy of the code, essentially. So the intended solution is this, basically. First, we must register and login with a given username. For example, you can register with the user Leo password test, and I'm going to do it in the background here. So I'm going to do, look, curl register, and it's going to say, okay, look, you have registered the user with this credential, Leo and test. And then I'm going to log in, and I'm going to save the cookie within the cookies.txt file. So now if I cut this file here, notice that I have this session cookie. Now this session cookie was generated by Flask, and it is used by Flask to handle authentication. And then I can actually use the endpoints with the -b flag of curl. So for example, in this file, I'm writing another file, hello2.txt with the content test. This other, I'm just reading the content that I wrote, test. And the intended solution is this one. As we saw before, is this EFBC8F. Is this like a unicode encoding, which is also encoded in URL for this case, of a particular slash. So we have checked the final flow, and we have made sure that it works. Now, if I remove the cookie file, for example, it should say you are not authenticated. And in this case, it says, look, you need to log in. So it checks for authentication. Now, to conclude the video, let's understand why does it work and what about unintended solutions. So let's first understand, okay, why does it work and what does this challenge want to teach after all, right? Well, this is the payload that we sent, but of course the interesting portion is this one, is this EFBC8F. So these 3 bytes actually represent a special Unicode character called full width solidus, and we can check it in this page code points. Basically, it is this character. Now, this character looks like a slash, like a forward slash, but it is not really a forward slash. So while it does look like a slash, it is not actually a slash. Now consider in the read, slash read, and look here in Emacs, you can see, because if I put a slash here down, you can see that these 2 characters are different. So this one is a little bit thinner, it's a little bit more inclined, so they do look different. Like you can notice it graphically that they look different. Now consider the code in slash read. First we do the check, then we normalize. So first we perform the check, and the check does not trigger the error, as the string does not contain slash, rather it contains this other character, which looks similar to a slash, but it's not really a slash. Then we perform the normalization. Now, during the normalization process, the slash character is actually mapped into the closest ASCII form, which is the normal slash. And we can check that easily with a simple Python 3 shell. Why? Well, because we can say import unicode data, like this. And then we can say normalize, and here I put this weird character. And when I do this, notice that I get back a normal slash. It means that when this weird character is normalized by this particular algorithm, the NFKC, it becomes a normal slash. So like basically what I send in input is something like this. It's literally like this one, flag.txt. This one, of course, bypasses the check, but when it gets transformed, it becomes this. And this, when it is added to the public path, will allow me to read the actual flag. So basically that's why it works. Thus, we can actually use the character to read the file. We're bypassing the slash and we're reading the flag. So that's the intended solution. Now, what about unintended solutions? Because, okay, the idea is that, sure, this works, but software systems are complex. They are one of the most complex systems that you can imagine. And here with complexity, we simply mean number of possible states. Like how many states can my system be in? 4, it's a simple system. 10, it's a simple system. Well, with software systems, this number becomes so huge that it's really hard to comprehend. And complexity is linked with the number of states of a system. Now, sometimes it can happen that a challenge that was designed with an intended solution actually has unintended solutions, which are ways of reading the flag of solving the challenge that were not originally expected by the author of the challenge. And to be honest, the existence of an intended solution should not surprise anyone, because that's hacking's ultimate objective. That is, hacking's ultimate objective is the discovery of unintended effects, of understanding the workings of the system so well that you can make the system do something that it was not really originally intended for that particular system. So really, even in CTF, which have the goal of teaching us how to think about unintended effects, sometimes we see real, sort of like naturally arising unintended effects, because the challenge is complex, it involves complex technologies, and there are many ways of solving the challenge. Now, I'm not sure if in this simple challenge that I show there are unintended solutions. For now, I didn't see anyone, so maybe if you find them, please let me know. I'm very curious. But basically, that's the idea. And here I put some reference with respect to Python Flask, the technology we use to implement the challenge, and the concept of Unicode equivalence, which was the key to understand this challenge. The key is that sometimes Unicode characters are mapped into ASCII characters, and Unicode normalization becomes a security issue when there is a mismatch of timing when we do the check and when we do the normalization. The problem is that normalization will change the data that we are working with. This means that if we do a check before normalization, we must also do it after normalization, because during normalization, the data changes, and therefore the assumption that we had about the data can change too, and some assumption can break. Like the assumption, is there the slash in my input? Maybe before the normalization there was not slash, but then after the normalization a slash came in, because it was normalized from a Unicode character. So I hope this video was fun, I hope it was interesting. If it was so, let me know in the comments, give me some feedback, subscribe to the channel, and share this video and this channel with like-minded people to help me grow. Thank you very much, and to the next video.